read along with Dr. Powell in the book Discrete Perspectives on Mathematics, section 1.1. Okay, this is functions on sets. This section kind of introduces the idea of what discrete mathematics even means. Notice these questions right here that appear at the beginning of the section. This might kind of give you some sense for what this section will be tackling. Notice that up here it says questions that guide the story. A story? Like, what do you mean? Well, it's a logic story. Every time you build a puzzle, you're putting in one piece at a time, and the sequence or order of the puzzle pieces coming together is like a journey or a story. And when we learn or study mathematics, there are different logical pieces that build up on top of each other or from side to side or in different arrangements around, but in a particular order. And that order is a story. And depending on how we do it, enables us to remember things in different ways better, perhaps if we can arrange the logical sequence in some good way. Okay, so that's what we're going to start with, and as we go along, we'll kind of hit some of these other questions as we go. So first of all, what is discrete mathematics and what does that even mean? As we look at section 1.1, go ahead and read through this. Discrete is an adjective, usually describes a set or a collection of things. And it's applied to a set of numbers often when we kind of lose any kind of sense for things being close together. So discrete means things are never thought of as close together. Notice that I have a number here, which looks extremely close to this one over here, but they're different. So if we have a discrete perspective of this particular set, or we think of it as a discrete set, maybe the set of real numbers, if we think of it that way, then all of a sudden, we're not thinking of these things as being close together. Because they're different, they are far enough apart that they can't be close. So that's the idea intuitively of what it means for something to be discrete, in particular a collection or a set. Now we're going to be thinking of, in this class, we're going to be studying things that deal with discrete sets or discrete perspectives of sets. And one of those tools that we use to study sets is functions between sets. So a function is kind of like a mapping tool that we can use between two different sets. And we give those sets different names. We call one of them a domain. We call another one of them codomain. Notice I'm not using the word range here because I'm not. Codomain is not range. Instead, I want you to think about this domain and codomain, if you're familiar with programming at all, as data types, like integers or floats or something like that. And so what do you need in order to define a function is you need to know what the data type of the input is and what the data type of the output is. That's the first thing you need to know. The next thing is you need some kind of algorithm or rule process or something that takes the input and does something with it and produces an output. Essentially, that's what a function is. It has all those parts. Even in mathematics, not just programming, we have this idea of data types, but we call them by the names domain and codomain. Codomain is the data type of what comes out of the function, and domain is the data type of what comes in. So we'll need those, and we'll be looking at some examples of that as we go along through the text. Okay, a function is well defined if the rule given for f is successful at taking each label in the domain set and telling us exactly which label to change it to in the codomain set. So every point in a set has a label, like in real numbers, and the labels are just the names of the numbers if every number is a point in that set. So you can kind of think about points and labels in a little bit, and that's actually in this in these paragraphs up here a little bit. And what that means is basically, if you have a set, everything in it is like a point, and and everything has a label. Now, what functions do is they kind of play with the labels a little bit. And if you make two labels the same, all of a sudden, it becomes the exact same point. So a function is a relabeling of a set. So you take labels in the domain and you play with them a little bit, and so if something is labeled with something in the domain, then the function is a rule that says, well, wait a minute, let's relabel it with this other thing that's in the codomain over here. Okay. So you can kind of think right here, I have a little bit more of a description of that idea. So a set consists of points. Each point has a name or a label. A function is a process by which one can change the labels of all the points in a domain set. Points are uniquely determined by their labels. If two points are assigned the same label, they become the same point. This is called merging. So let's look at an example of merging in a picture. Okay, so here's an example of a function. All right, so you could say that the domain are the letters A, B, C, and D, the lowercase letters A, B, C, D. Now, the codomain could be the whole alphabet in lowercase, or the whole alphabet in lowercase and uppercase. Notice that the outputs do conform to such choices of data types. So really, there are lots of different codomains that could work for this particular function rule that we have. So looking at this, if we have so what's happening here is we're replacing the label A with something in the output in the codomain, a label E. Notice that the domain is everything that goes in. The whole set of inputs is always the domain for any function, so it kind of conforms to whatever the data type is. So this data type is rather small, just A, B, C, D. The codomain could be a lot larger. But as we're going along, notice that so A now has the label of E. So we cross out A and have a label E. B cross out has a label of F. C cross out label of G. D cross out label of E. But notice we have a merging that has to go along. A and D actually go to the same place. So you could think about a function as being kind of like a morphing mechanism. You take a set and you morph it into another one. And we're going to be looking in this class at functions, or in this textbook, at functions that that morph sets in such a way that they preserve certain types of structure that that are inherent in the domain set to the codomain set, but through this relabeling merging type process. Now, as we do this, we like to have some names of sets. So here, N, natural numbers, just the counting numbers, 1, 2, 3, 4, 5, etc. So basically integers that are positive. That's what natural numbers is. We use this symbol N, this kind of with these double lines in the middle. Rational numbers, Q, quotient. Quotients of integers, fractions, basically. Any kind of fraction is a rational number. So we have an example here. We define a function whose domain is the set N, the codomain set is Q. Okay, suppose we have a function like this with domain N and codomain Q. That means it goes from counting numbers 1, 2, 3, 4, etc. Those are all inputs for this function. Output could be any fraction. Okay, So let's suppose that the function rule for the output is we input x and we output x over 2. So we're inputting a counting number and we're going to be outputting whatever that is over 2. This function is well defined because for each counting element in n, x over 2 happens to be a fraction. So that would work. Here is some notation. This is an assignment arrow. Okay, we have x maps to x over 2. So input, and then that's the output. This is another way of writing down the function rule or algorithm. We don't have to necessarily write down f of x is equal to x over 2. We could use this notation and just know what the domain and codomain are, and that's enough to say what the function is. Okay. So for instance, okay, let's take a look at some more definitions. So z is not just the counting numbers, but negatives and zeros. So all the integers here. Z is a symbol for that set. C is a symbol for the complex numbers, a plus bi, where I is a square root of -1 and a and b are real numbers. Okay, so let's take a look at this example. So we have a function that goes from integers to real numbers, and it's given by this particular rule. X maps to the square root of x. So the question is this function well defined? Let's see, we're going from integers to real numbers. Well, wait a minute. If we put in negative integers, we're going to not get something real. So that means we get an error because the square root tries to give us something that's not in the right data type for output. So it's not well defined. So that's an example of something not being well defined. Cartesian product. What is this? Well, we can take two sets and make a new set from those sets. So we get another set out of it. Basically, this just means that you're pairing things together. So don't think of this as any kind of fancy operation. All we're doing is we're taking two sets and basically thinking of ordered pairs with like 2, 3. Notice that 2 and 3 are both integers because see, z cross z. This means that the first component of this ordered pair is an integer, and then the second component is also an integer because we have z cross z in that particular case. So we can define functions like this. Let's suppose we have a function where the domain is z cross z and the codomain is z. And let's suppose that we define it this way. Well, this is not well defined because x over y does not always give an integer. And in this particular case, and not only that, you also know that integer over 0 is never well defined either. It's never an element of z, and it's never an element of r. So no member of this subset z cross 0 or the domain consisting. Okay, so this could never even work. Of course, there's other examples that won't work as well because we're going to the integers. Perhaps in this example, if I had put an r here, I mean, we would still have the same issue, the same problem going on because you can't have something over 0 because 0 is an integer. Okay, so let's take a look and keep going here to the, we're going to keep going to the next subsection, but we'll end this little video here. And thanks for watching. We just kind of started the first subsection of section 1.1, and we're going to go on to the next subsection in the next video. Thank you so much for watching.